Today's lesson is going to be a quick review of how we did those baseball problems from last class, remembering that the first two are going to be graded. The third was a challenge or a bonus question. I'm going to show you how each of those are solved, and then I'm going to go into a quick mini lesson about multiplying radicals. The majority of the class today I want you to be spending doing on the project I assigned last class, so make sure you're looking on the classwork tab and finding that. It is not an Edpuzzle. Make sure you read all the directions. If you have questions, send me an email. If you want to do a Google Meet, just let me know, and I'd be happy to help. All right? So we're going to get ahead into the baseball problem review. I'm going to go through this a little bit quickly. If you need to watch it again, feel free. The first question, question A on that assignment, was how far is it from home plate to second base? Well, we can use the fact that we can create a right triangle using the baselines. So from home plate to first base is 90 feet. From first base to second base is 90 feet, and we have a right angle right here. So when we're looking for what it is from home plate to second base, we're looking for that value, which is the hypotenuse. Since these are both 90 feet, they're isosceles, this is a 45, 45, 90 triangle, one of those special triangle relationships we learned last week. So you could totally do the Pythagorean theorem, 90 squared plus 90 squared equals c squared, and solve it. Or you can just remember that the 45, 45, 90 triangle tells us that x is going to be 90 radical 2. As long as you explained it or you showed your work, either way I would have been fine with you solving it. 90 radical 2 has a decimal form that will help us in a later problem, but we'll get there when we get there. So the next question was asking how far is it from the home plate to the shortstop? Now, for those softball and baseball players or appreciators out there, you know that the shortstop is between second and third base. And for the purpose of the problem, they're directly between second and third base right on that baseline. So they're going to be 45 feet away from third base, which makes a 90-degree angle. So once again, we're looking for the hypotenuse. We know that that's 45. We know this is 90. So when you plug that into the Pythagorean theorem, 45 squared plus 90 squared equals c squared. When you solve that and you do all the math that goes into it, you would get 45 radical 5. I'll show you quickly how I got 45 radical 5, and then we will move on. So 45 radical 5 is coming from doing the Pythagorean theorem. 45 squared is the first calculation you have to do, which is 2025 plus 90 squared, which is 8100. When you add those two numbers together, big numbers we're dealing with here, you get 10,125 equals c squared. Then we need to take the square root of both sides. 10,125 breaks down into 9 times 9 times 5 times 5 times 5 when you do its prime factorization, or just factorization. I know 9s aren't prime, but 9s can leave and 5s can leave, so it's 9 times 5 times radical 5. So the distance here would be 45 radical 5. Once again, I know I'm going through this kind of quick. It's more just as a quick overview for you to see maybe where you went wrong or if you did it correctly. All right, now I'm going to go over that last challenge problem. And I have a few notes already drawn here. So in that problem, it told you that from home plate to the pitcher's mound was 60.5 feet. And from question A, the first question we just went over, we know that from home plate to second base over here, that full diagonal is 90 radical 2 feet long, which I found its decimal version, which is 127.28. Now, if I know it's 60.5 feet from home to the pitcher's mound, and I know the whole length from home to second base is 127.28, I can just use subtraction, 127.28 minus that 60.5 to figure out the distance from home plate to second base. When I do 127.28 minus 60.5, I get 66.78 feet. So that's the distance from the pitcher's mound to second base. 66.78 feet. So now we're going to go ahead and try to figure out how far is it from the pitcher's mound to first base. Now, whatever we get in this answer is going to be good because it's going to be the exact same answer as it is from third base to the pitcher's mound. So if I'm looking for the pitcher's mound to first base, what I need to figure out is, first I need to figure out how far is it from first base right here to the exact center of the baseball diamond. I already know that the full length from one base opposite the other is going to be that same number we got from home to second. It's going to be 127.28. So if I want to find out just what it is for this leg of the situation, I'm just going to take that 127.28 and I'm going to divide it in half. When I do that, I get 63.64. All right. Then the next number I'm going to need to be able to figure out how far it is from the pitcher's mound to first base is this little piece right there. Well, there's a way to figure that out because if I know that the halfway point is going to be the same as that number 63.64, and I know that from home plate to the pitcher's mound is already 60.5, that little piece we're dealing with is going to be 63.64 minus 60.5. When you do that, you get 3.14. So now we have the two legs of the right triangle, and we can use them to find x. So we can do 3.14 squared plus 63.64 squared, and that will equal c squared. I will do that calculation now. This one is a really big number. It's 4,050.05. I'll round it to 3.14 squared, which is approximately pi, is 9.8. I'll round it to 9.86, which equals c squared. We're now going to add those two numbers together. 4050.05 plus we get 4,059.9 equals c squared. The last step is we'll take the square root of both sides. Now this can't be simplified because it's in decimal form, so we'll just get a decimal answer. So the distance from the pitcher's mound to first and the pitcher's mound to third is both the rounded decimal of 63.72 feet long. I'd be happy to work with you guys to explain that in more depth, but I wanted to just do a quick overview for it for those of you that just didn't understand where I was coming from. If I'm being perfectly honest with you, when I did this first, I got it wrong. I oversimplified. I didn't realize how many steps there were to this question. Once I realized how many steps there were to this question, that's when I made it a challenge problem. So hopefully that explanation made a little bit more sense. Either way, as long as you understood how I got A and B, if you didn't get the third one, that's okay. All right, so now we're going to move into just a quick mini lesson on radicals, specifically what happens when I have a radical squared. So if I have the square root of 7 squared, whenever I have a square root and then it's being squared, those are inverse operations of each other. Very simply, they just cancel each other out, and all you're left with is the number that was inside. So if I have the square root of 9 squared, that's the same thing as just 9. If I have the square root of 11 squared, what does that equal? 11. If I have the square root of 103,324 squared, that very simply equals just 103,324. Oop, could have made that 4 a little cleaner. There we go. And then one other thing I want to introduce you to is what happens when I'm multiplying radicals that aren't the same. So what if I'm doing the square root of 3 times the square root of 2? In that situation, you just put them and multiply them under the same radical. So that becomes the square root of 3 times 2, which is just the square root of 6. Since the square root of 6 doesn't get simplified any further, we just leave it as the square root of 6. So now you give it a try. If I give you the square root of 7 times the square root of 5, what answer do you get? You get the square root of 35. Can that number be simplified any further? No, it can't. It stays as the square root of 35. Let's try 2 more, and then I'll leave you the rest of time to work on your project. What if I have the square root of 10 times the square root of 6? That becomes what? Becomes the square root of 60, but the square root of 60 can be simplified. 60 breaks down into 6 and 10. 6 breaks down into 3 and 2. 10 breaks down into 2 and 5. So that breaks down into 3 times 2 times 2 times 5. We have a pair of 2's that can leave. And everything that's left is 3 times 5. So that is 2 times the square root of 15 as our final answer. I'm going to give you two practice problems like that, where you're going to multiply them together and then try to simplify them, and then that's going to be it for today. All right, so we have the square root of 8 times the square root of, let's go with 12. Now in this situation, neither of these numbers are even simplified, which is kind of tricky, but that's okay. This becomes the square root of 96. 96 can get broken down a couple different ways, but why don't we just break it down into the factors we already know? 8 and 12. 8 gets broken down into 4 and 2. 4 gets broken down even more. 12 also can get broken down into 4 and 3. 2 and 2. I see a pair of 2's and a pair of 2's. So I know 2 things are leaving. How many 2's are there total? 1, 2, 3, 4, 5. And a 3. 2 pairs of 2's leave. A pair of 2 is left. Sorry, not a pair of 2's, just a regular 2 is left and a regular 3 is left. We have to multiply those together. 4 radical 6 would be your final answer. And one last one for you to try. Square root of 6 times the square root of 3. Try that one out. That becomes the square root of 18, which breaks down into 2 and 9. 9 is a perfect square of 3 and 3. So then we can break it down into 2 times 3 times 3. The 3's leave, giving us 3 radical 2 as our answer. All right, guys, I hope that went well. A couple of those things might be helpful in terms of understanding your project today, so keep working on that. It's due by 8 o'clock tonight, and if you have any questions, just shoot me an email. Looking forward to hearing from you. Have a great day, guys. Bye.